When we talked about limits, we saw that in a lot of cases we can find limits by just plugging in the number. When this happens, we give it a special name. We say a function f is continuous at some number x equals c if three conditions hold. First, the function needs to exist at c. F of c has to exist. A function is not going to be continuous at points that are not in the domain of the function. Point 2, we need the limit to exist. If the function doesn't have a limit at a point, it doesn't exist. It's not continuous there. And 3, these two things that we just said exist have to be the same thing. The limit as x goes to c of f of x equals f of c. Now, sometimes people will write the definition of continuity just using this last statement here, and kind of just by writing that statement, they're kind of implying that these two values exist. But sometimes it can be quite useful to be able to break down why something is not continuous at a point, basically by stating which one of these fails. Because it could be possible that both the function exists somewhere and that its limit exists, but they're not equal, or it could be that one of these two doesn't exist, and so we want to be able to distinguish those different cases. Now, we can talk about more than just a single point. We can say that f is continuous on an open interval AB if it's continuous everywhere in that interval. So it's continuous at every point, or every c inside AB. So remember, the open interval here is just the set of all numbers between a and b, not including a and b. And for every single number that's between a and b, we need f to be continuous at those numbers. If it's continuous at all those numbers, we just say, just to make it easier to talk about, we just say it's continuous on the entire interval. For closed intervals or half open intervals, so something like closed interval from a to b, this now includes a and b. Or it can have half open ones where we either have a but not b, or b but not a. In those cases, we do not need it to be continuous completely at the endpoints. We need it to be continuous everywhere between a and b, but we only require the function be continuous from one side. So we talked about one-sided limits in the last section. If we were, say, talking about the closed interval from a to, or the half open interval from a to b, this one here, we would need to have that the limit from the positive side at a needs to equal f of a, which requires that f of a exists, and it requires that this limit exists, this one-side limit exists, and that those are equal. So if it is continuous on the open interval a to b, so it's continuous everywhere between a and b, and then this additional condition holds, then we'd say it's continuous on this half open interval. And the similar definitions for the other closed interval, for the other ones where we include the endpoints. Whatever endpoints that we're including, we need to be able to have the one-sided limits. For a, that would be from the positive side, from the right, but for b, it would be from the negative side, from the left. Now, informally, what we're really talking about when we talk about continuity here is that when we trace the graph of the function, we can do so by not picking up a pencil. So let's say, we're talking about a function from a to b, I can just go ahead and trace this whole thing without having to lift up my pen or pencil. If this was not continuous from a to b, then that couldn't be done. There'd be some issue that would actually get in the way. And we'll get into what possibilities there are for those kind of issues a little bit later in this section. But first, let's talk about some examples of functions that we know are continuous. One, polynomials. We already saw in the last section, when we talked about limits to begin with, that if p of x is a polynomial, and then we take the limit as x goes to c for p of x, we always get p of c. That works for every real number c. So that means that any polynomial is going to be continuous on the entire real line. We could write that as the interval negative infinity to infinity, or we could write that as our fancy r, however we want to write that. I'll probably just say whenever we talk about this that it's just continuous everywhere. So polynomials are really nice when it comes to continuity. The second category here we have here are rational functions. I defined these last time, but go ahead and define them again here. A rational function is any function r of x that can be written as a polynomial divided by another polynomial. So p and q are polynomials here, and r is a rational function that's just made by dividing those two. Sometimes they don't actually look like that. Sometimes you can actually have, say, one fraction like this plus another fraction like this. Because we can combine fractions and put it in this form, that's still a rational function. So it's slightly broader than what I've written here, but every rational function can be written in this way somehow. Might have to do some algebra to put it into that form, but that's not really the point. The point here, though, is that because with polynomials, we can take our limits by just plugging in the c, when I take the limit of something like this, I can go ahead and plug in the c for p of x and plug in the c for q of x, and that just gives me the value of r at c. The only problem here, though, of course, is what if q of c equals 0? If q of c equals 0, then we can't do that. I mean, we're basically saying that the limit of the bottom would be 0, and so we can't use our rule from the last section that says we can just take the limit by dividing the limits at the top and bottom. But in that case, c is not even in the domain of r in the first place. R of c wouldn't exist then. So if q of c equals 0, R of c does not exist. Basically, we're saying that c is not in the domain of the function. But any place that is in the domain of r is a point where q of c is not 0, and so not only does this r exist, it also, we can take the limit by plugging in c, just using our rule from polynomials. So we can say here that r is continuous at every point in its domain. As long as we're in the domain of the function, we are continuous. So really, being able to say where a rational function is continuous is exactly the same question that we had before of what is the domain of the function. We can answer both those questions at the same time, which is really nice. Now, for this next category, I'm getting a little ahead of ourselves, but it will turn out later that exponential functions, these are going to be continuous everywhere. So just like with polynomials. And logarithms, these are going to be continuous specifically for positive numbers. So I should put on the interval from 0 to infinity. Because that's the only place where the logarithm is defined in the first place. We don't have logarithms of 0 or negative numbers. But we'll talk about those functions more specifically later on in the course. I think we have a whole chapter on those. But I just want to kind of include them here just to kind of give us the whole breakdown of these building blocks that we work with a lot in this course, and how they deal with continuity. I'm going to go also include as a fourth one here. This is getting a little outside of what we're even going to be talking about in this course. We can talk about trig functions. The sine and the cosine. These are two fundamental functions in trigonometry. These are also continuous everywhere. Now there are a few other trig functions. There's actually 6 in total, including the sine and cosine. But the other ones get a little bit more complicated. They actually have a lot of places where they're not continuous. And I don't want to get into that more than we've done here. In fact, we can get all the continuity of trig functions based off of what we know about sine and cosine, but just not in this class. But really what you can see from this already is that a lot of the functions that we're going to be working with, in fact, pretty much all the functions that we work with, have very nice continuity rules. They will be continuous at basically on their domains. In all these cases that I've written these down, everything I've written is not only where they're continuous, but also what their domain is. So really, in order to kind of break that pattern, we have to do something special. Let's go ahead and take a look at some examples, though. So here we're basically trying to should probably basically write down what the book's instructions here. Determine where functions are continuous. Technically, the instructions here are a little bit more detailed than that. It says describe the intervals on which the function is continuous, explain why the function is continuous on the interval, and if the function has a discontinuity, identify the conditions of continuity that are not satisfied. So we haven't really defined what discontinuity means. It just means that where is the function not continuous, and describe why it's not continuous. Problem 16. We have a function f of x is equal to 3 minus 2x minus x squared. Where is this function continuous? Now, we don't have to prove much of anything here. We just need to identify what's going on from our categories. And since we're not going to be dealing with 3 or 4 at this point in the class, we're really kind of looking at, is this a polynomial? Is it a rational function? If it's not one of those, then we actually have to do more work. But this function right here, this is a polynomial. In fact, it's a quadratic, if we want to be even more specific. So that means it's continuous everywhere. And that's all we have to do. If we can recognize that something's a polynomial, we already know immediately that it's continuous everywhere. So let's kind of crank it up a little bit then. What if we instead have something like that? This is a rational function. It's the polynomial x minus 3 divided by the polynomial x squared minus 9. With a rational function, basically this question boils down to what is the domain of the function. The domain of this function we can determine by figuring out where the denominator equals 0. So where is x squared minus 9 equal to 0? If we solve for x, we have x squared equals 9 by moving the 9 over. We take the square root. Remember, when we take the square root, we do need to put in a plus or minus, but the square root of 9 is 3. So that means that this function here is continuous at every number except for 3 and negative 3. If we want to write that down as an interval, they did say in the instructions specifically that they wanted intervals, but we do something like from negative infinity to negative 3, it's continuous. At negative 3, we have a problem, but then from negative 3 to 3, it's continuous. At 3, we have another problem, and from 3 to infinity, it's continuous. That's not only the domain, but it's also where it's continuous. What if we look at another rational function? Let's look at problem 20. Here our function is 6. So 6 itself is a polynomial technically. There's no x's there, but constant functions like 6 are polynomials. On the bottom we have x squared plus 3. And we want to determine where is this function continuous. And like I said, it's a rational function. So we just need to determine what is the domain of the function. And that just boils down to where is the bottom equal to 0. We have to exclude any point where the bottom equals 0. But if we bring the 3 over this time, we have x squared equals negative 3. And since we don't want to use complex numbers here, we're just dealing with real numbers in this class, we can't take the square root here. In other words, the bottom here is never 0. In fact, you might have been able to notice that from the beginning, because x squared is always a non-negative number, and if we add 3 to it, then we always have a positive number. We never equal 0 on the bottom. So this function here has domain all real numbers, and so it's continuous for all real numbers. It's actually a fairly nice function. If we were to go ahead and plot that function in problem 20, we had 6 divided by x squared plus 3, not 63, 3. And we just have this function here. It's nice and smooth. There's no holes in it. It's just a very nice function. If instead we looked at the problem 18 function, in that case we had what was x minus 3 divided by x squared minus 9. And I messed that up. I decided to put the minus 9 in the exponent there. X minus 3 over x squared minus 9, we get this function here. Notice on f, the problem 20 function, I could just kind of trace that out and never leave my function. But for g, the problem 18 one, I definitely have to leave the function when I'm at -3. I have to jump from down here all the way up to here to continue tracing the function. Now, one thing that you can note from this graph is that even though we do have a point where the function is not continuous, this function does not have a value at 3. That place where it's not continuous is not really shown here. There technically should be a little gap here at 3, but GeoGebra doesn't show things that are that small, because this function does exist everywhere around 3 and exists very nicely around 3. It just isn't fine enough to show that. We'd actually have to go ahead and maybe put in the point at 3. So something like 3 comma, do g of, well, I can't do g of 3. I need to know what the value is there. I think it's 1/6. Yeah. And I might even change the look of that. Here. Yeah. Let's make it, just put a little white circle there, just to show that that point's not really on the graph. There is a hole there that we technically have to pick up our pencil and skip over if we were to draw that graph. So don't always trust the graph, even if you have it drawn out, because it could look like something is continuous at a point, even if it's not continuous there. We'll discuss the differences between these different places where the function is not continuous in a little bit. But let's move on to another problem. Let's look at problem 27. This will be a little bit more complicated than the ones we've been looking at so far, because it's not going to be a polynomial or a rational function. It's actually going to be a piecewise function. We have one formula, -2x plus 3. That's going to be true as long as x is between -1 and 1. And then x squared is going to be the function when we're between 1 and 3. So first we can note that we do have polynomials as our pieces. So that means as long as we're on the inside of these intervals, it is continuous. So at, say, 0, at 0 it just looks like the line -2x plus 3. That line is continuous. And so it's going to be continuous at 0. It's actually going to be continuous all the way from -1 to 1, including -1, because we are allowed to take one-sided limits there. But we can't really talk about 1 quite yet. So just from the fact that we know we're dealing with polynomials on the pieces, we already know it's continuous on -1 to 1, not including 1, and because we're dealing with x squared from 1 to 3, we can say it's continuous from 1 to 3. Again, still not including 1. If x is if x is below -1, so like say at -2 or something like that, then we don't have a definition for it. Same thing if it's above 3, so at 4, 5, and so on, there's also no definition for those points. And so remember, that's our first condition for continuity. We actually do need to be in the domain of the function. So -2 and 4, those are both outside our domain, and so it cannot be continuous at any of those. The only point that's left that we haven't actually messed with yet is what happens at 1. 1 is where these two intervals connect, and we can't really talk just about the one-side limits because we have both the limits. At -1, since there wasn't any function below -1, we didn't have to talk about the limit from below. As long as the limit from above, the limit to -1 from the positive side, as long as that equals the value of the function at -1, which it does in this case, you can try that for yourself. As long as those one-side limits exist at -1 and at 3, we're good. But 1 does have points above and below it in the domain of this function. So we're going to have to test whether or not we actually do have a correct limit at that point. Now, we should note here that there is a definition for the function at 1. So in this definition here, we said we're going to use the formula -2x plus 3 when x equals 1. So f of 1 is just -2 times 1 plus 3. Of course, there we're taking -2 plus 3, and so we get a 1. So the function does exist at 1. What about its limit? Well, since we are dealing with a piecewise function, we actually do need to go ahead and use one-sided limits. So let's start with the limit from below. With numbers that are less than 1, now we're dealing with the -1 to 1 interval, and we're going to use the formula -2x plus 3. But now we're just taking a limit of a polynomial. So we can go ahead and find this limit by plugging 1 into our function. Or into this formula here, I should say. Of course, we already found that. That's equal to 1. It's the exact same thing that we had here. It's just like at -1, I didn't go ahead and find the one-side limit, but I knew that just because we're dealing with this linear function, this polynomial, I was able to just plug in the number and I got the value of the function. The one that we really haven't dealt with is what happens when we come at 1 from above. We're looking at numbers that are above 1. Now we're looking at numbers between 1 and 3. We're now using the formula x squared. Now, technically here we're approaching a number that's not in the domain of this piece of the function, but we're still working with x squared as a polynomial, and when we take limits of polynomials, we just get to plug in the number. So here we get 1 squared, which is equal to 1. And now the important thing here is that we got the same answer. So the limit from below is equal to the limit from above. The two one-sided limits are equal to each other. That means the limit does exist, and the limit is 1. And that limit is the same as the value of the function. We have f of 1 is equal to 1. So since all three of those things were the same thing, that's what we want. That's saying that f is continuous at 1. And so we kind of get to combine these two intervals. So it's continuous from -1 to 1, it's also continuous at 1, and then it's continuous from 1 to 3. And so it's continuous all the way from -1 to 3. This is a continuous function on that entire closed interval. Now, if this limit had turned out to not exist, if these had been different numbers, we would have to say put that and that separately and put a union between them, because at that point in the middle, we wouldn't have continuity. So there's various things to keep in mind there. Okay, I'm going to go ahead and stop this video here. In the next video, we'll talk about points where a function is not continuous, and we'll describe what possibilities we have there. And then we'll also describe a few things about what it means to be continuous. Some results that come from being continuous. So I'll see you in that video.